Hey everyone, thanks for joining today's Dynamo office hours. Before we begin, definitely wanted to plug our GTC DC event that's happening in a week and a half in DC. As you know, GTC is our annual flagship conference where we highlight all the latest innovations and developments across everything in NVIDIA, which is definitely a bunch. We have one in March in San Jose and then one in October in DC. And so if you're a developer and enthusiast who enjoys seeing what's happening, the latest in accelerated computing and AI, definitely highly recommend attending GTC DC. And you can scan this QR code here to register. All right. Okay, sounds good. So with that said, again, thank you so much for tuning into today's Dynamo office hours. Just to give a quick, introduction, Dynamo is a high throughput, low latency framework for serving Gen AI models and reasoning models at data center scale. So everything we do is constantly built for how we can optimize and do performance at the AI factory level. And so today's topic is going to be about building fault tolerance in such high scale systems, right? And so today I'm joined with some of our core engineers and experts across Dynamo and also in the fault tolerance areas. So my name is Anish. I'm a product person on the Dynamo team. Rest of the team, would you like to introduce yourself?
Nilay, you want to start?
Sure. My name is Nilay. I'm one of the architects on Dynamo and specifically looking at observability and fault tolerance.
Yep. I'm Ryan. I'm a core contributor on Dynamo and focus on fault tolerance today.
Hi, I'm Jackie. I'm another core contributor on Dynamo, focus also on fault tolerance today.
Awesome. As you know, Dynamo is an open source first project built in Rust and with Python bindings for extensibility. So we have a public GitHub where we constantly share our roadmap, what we're up to. All of our code is available. So if you have any questions, feel free to open up GitHub issues. We also have a Discord as well where we chat with community members. So if you have any questions you're not able to get to today, feel free to ask in the Discord. But with all that said, with all the kind of laundry items out of the way, how about we get started with the presentation? And to kick things off, obviously with Dynamo, we're constantly running stateful workers and microservices, across the board, right? And we know that fault tolerance is important, but was wondering if one of you guys could talk about why it's especially important in Dynamo and other high throughput, inference systems that run in production.
Sure. And maybe I'll take a first stab at this and kind of show some of the technology we've been working on. So one of the interesting things I think, when we look at Dynamo and some of the goals behind Dynamo, it's been really about system level performance. So things like how do you match decode phases of LLM processing with the prefill part? How do you do KV cache aware routing? And just like we need to think of performance from a system level, we also need to think about fault tolerance and observability from a system level. So just as we have multiple places in the system processing requests at any point in time, multiple components, we really need to kind of work through how we're going to provide fault tolerance in the system. So we look at kind of three areas. So detection and recovery, and our goal is really to essentially plug in to industry standards. So in terms of detection and recovery, we want to make sure that we're playing good citizens in Kubernetes deployments. So relying on the GPU operator to cordon off nodes and make sure that our workers don't land on those. From a metrics tracing and logging, we'll share some more details of this as we go through. But again, our goal is to be standard as possible, right? To give you the familiar tools that you're used to, but give you the visibility that you need. And finally, because the runtime stack is multi-layered, we also need to think not only from a system level, but even within a worker, we need to be thinking about how do we get visibility metrics and fault tolerance across different areas, from the LLM engine to the Dynamo worker that kind of wraps that to the runtime itself.
Yeah, and maybe just to add on to that, I think there's a lot of technology nerds out there like us who, look at something like Dynamo and they're just fascinated by, there's all these cool components. The concepts here are really fascinating, but when we move past our local deployment of a small model on our desktop or something, and we really push the boundaries of what we can do, like maximum throughput, minimum latency, serving real production use cases, then you start to care a lot about, you don't want this thing to crash. You don't want any downtime. And this is where we come in, because we are seriously aiming at massive scale data centers, multiple data centers, like different regions in the world. And downtime is a no-no. So we're happy to be helping keep that to a minimum.
That's exactly right. And, as we know, Murphy's Law, whatever can go wrong will go wrong. So we need to be able to handle faults when they happen and try to prevent them when we can. So I try to think of it, again, from a system level into 3 buckets. 1, detection, how fast we can detect software or hardware failures so we can react to them and start the recovery process as quick as possible. How would we even prevent overload of the system? So how do we prevent the system from getting into a failed state? And as we'll talk about, we'll also look at how do we respect cancellation. So not all requests actually are meaningful. So as we know, when we're working with large language models and chats, sometimes we interrupt it in the middle. Because of that, we want to make sure that we're not wasting GPU resources or computation resources finishing a request that the user doesn't care about, right? Now, that's on the detection side. When there is an issue, we want to be resilient to it. So we want to be able to route around failures and migrate requests. And we've got some really cool demos that show that in action. We want to be able to keep operating at a degraded performance while we go into recovery and make sure that there's no cascading failures. So we're going to talk a little bit about high availability and some of our testing around that. And finally, the last piece is recovery. So we know that issues are going to happen, no question. When they do, we want to be able to recover as quick as possible. And we're starting to do research some technologies to make that quick as well.
All right, let's dive right in. Let's figure out how we're doing all 3 of these buckets in Dynamo today and how we're thinking about things.
And Jackie, I'll hand it over to you to go over the requests flows.
Thanks, Nidhi. So for request migrations, so why do we want request migrations? Because just like Nidhi already mentioned, that faults can happen as we are scaling up our design and data into a data center. And in a data center, we have many nodes and GPU, and then definitely things goes wrong. Maybe that we get a node that power off. For example, in the diagram, we have the client, front end router, and we have a decode worker and another decode worker. So maybe the first decode worker, for some reason, it has a power failure, or some reason it got unplugged from the network, or simply we find out that maybe we want to migrate the worker to a different part because for some reason, we got clicked out of the current part, or maybe we found the second part to be cheaper just because we just want to save money all the times. But in either case, if we are migrating, we don't want to tell the user that, hey, your request just failed because we are migrating a part for whatever reason. We want to make sure the user is still seeing the request is continued and finished in the normal way that's like nothing has happened. So let's talk about like how migration works in Dynamo. So right now, let's say we're worker 1. So we got request token 0 and request token 1, and worker were generated response token 0. And then for some reason, the worker got disconnected. And in this case, if we don't have migration, the user is going to see, oh, they got response token 0 and the sentence is not complete. This is not what the user wants to see. So we have migration. And migration, what it does is takes token 0, token 1 from the request, and then the response token 0, put it into a new request, sends to worker 2. That's where you see at the bottom of the slide, you got request token 0, request token 1, and response token 0. Then worker 2 just takes from there and keep generating response token 1, response token 2, and then towards the end of generation. So how about we see this in action? So can you pause real quick once we get into the, yes, thanks. So on the demo, we have worker 1 and worker 2 at the bottom left and bottom right terminal. And then we also have the front end started on the top left of the terminal. And we have the client on the right side. So what will happen next is the client will send a request to the front end. And then the front end will route the request to either worker 1 or 2. But through the magic of like a pre-recorded demo, we know the request is going to worker 1. So what we will do is we will stop worker 1. That just simulates a failure. And then we want to see the request getting migrated to worker 2. And then on the client, we want to see nothing happens. It's just keep responding towards the end of completion. So let's play the demo, shall we? Okay, so here we are at client, and we're going to send the request. Now you see the request is going, and worker 1 received it, and we just killed it. And then worker 2, you can see it gets the new request ID, and then we can see the migration happened. And you can also verify at the front end that we see that stream got disconnected, and we are recreating the stream.
Wow, that was fast. I couldn't even tell that a failure happened.
Yeah, maybe we can just go back to the last slide. We can have a better view for the audience.
I think that's the goal here, right? We don't want the users to know that a failure happened either. So
Cool.
sounds like we've achieved it.
There's one caveat here that I'm curious to ask about, which is, I know that in our current request migration, we, migrate the intermediate tokens, but there's still the KV cache that has to be recomputed now in the new worker, right? So I guess first to begin, why is it so hard to migrate the KV state? And two, are we going to do anything to optimize there as well?
Yes, speaking about the KV state, right now when we do the migration, we don't migrate the KV state just yet. We just migrate the state of the request and response. And right now we have a KV block manager that's in progress. I think Nile can talk more about it. And basically our next goal is to also have the KV cache migrated from the worker if we're able to retrieve it and put it into the new worker so that we don't have to recompute everything we already have. We can just continue off straight from where we have.
Yeah, that's exactly right. So I think, we're wanting to leverage some of the other technologies that Dynamo brings, in particular the KV block manager, which will provide an easier way to do bulk transfers of KV state. So I think that's the biggest thing is that what we're doing here is we're basically storing tokens, right? And they're relatively small compared to KV cache. It would be kind of prohibitive if we wanted to store KV cache in CPU memory while all the requests were going. But each individual worker could offload it and then share it through KV Block Manager. Okay.
Cool.
Should we move on to cancellation?
Sure, thanks, Nile. So moving on to cancellation. Now, once we get the serving scale up to a data center scale level, we have many more worker and many more components. So for example, if we are just doing VRM serve, we only have the client and the front end. That is the left two boxes on the graph. And then if we want to cancel, so if the client somehow disconnects from the front end, the front end will receive it, and the front end is also the engine. So we will also be able to turn everything off and then not wasting any GPU resource when we have canceled the request. But once we scale this thing up to a data center level in Dynamo, then we can't just cancel the front end because the engine is no longer at the front end. It's with the decode worker and preview worker if we are doing disaggregated serving. And then if we just cancel the front end, the GPU is still being used by the decode worker, and that's causing money. So we want to not waste those money that if the user is no longer anticipating for the response. So we have request cancellation. What it does essentially is if the client is disconnected from the front end, we will cancel the request downstream to the decode worker. And if we have preview worker, we also cancel that preview request at the preview worker if it's still running. So that's really ultimately saving you money if the user were to cancel. So maybe let's move on to the demo. And in this demo, we have on the left side, yes, please pause it. Thanks. So on the left side, we have the client, and then in the middle screen, we have the worker that's already up and running. And on the right side is NVIDIA SMI that's trying to show you the GPU utilization. And on the right, currently we see it's at 0%. So what we will do next is we will send a request to the server, and then to begin with, we just want to show the GPU utilization goes up without any cancellation as a reference. So just send it, and then we can see we get the new request, and then the GPU utilization goes up to near 100%. And then let's wait. Yes, the request completed, and then we can see on the engine, the request has finished, and then it's clear that the GPU utilization has dropped to 0. Next, we are going to send the request again and cancel it. You can see the GPU utilization goes up, and we cancel it. Now, immediately, the GPU utilization goes to 0. And then on the engine, we can verify the request has been aborted. So the GPU resource is saved for other requests, if there's any.
Yeah, Jackie, I have a question for you on cancellation. What's like in your demo, you kill it to demonstrate the feature, but what's a realistic scenario that cancellation would actually happen? Like, why are requests getting canceled?
There are many cases. For example, if the user is on a mobile network and then they are waiting for a response, and for some reason they walk into a signal dead zone, then the user is disconnected. In this case, the user cannot actually receive the response from the engine. Then we want to cancel it, and then we wait for the user. If they comes back into the connection, then the user can resend the request, and then we can have another worker just to carry on forward.
Yeah, I think there's also just examples where you're in the middle of a chat and it's just going the wrong way, right? Like the LLM's just going on a tangent and you want to cut it off immediately in the middle. This gives you the ability to do that without having to continue and finish it on the back end, right? So it's kind of like, as soon as you realize on the front end that it's no longer useful, we want to be able to stop all the back end work as well.
Got it. Looks like we have a question from the chat here on request migration, perhaps. I'm not sure if I can see the whole thing, but Jackie, this one's really, there it is.
Yeah, I can read it out. How are deterministic sampling params, like top K, I'm assuming, temperature, seed, etc., preserved when you're rebuilding the token state during the migration? And how are possible deviations in the token stream minimized when you're continuing with the same state but in a different worker?
Yes, I can take that question. So in terms of the configuration like temperature or token, we actually cache those values when the request initially arrive at the front end, and the front end is responsible for detecting if the worker has dropped out and we need migration. So basically in the diagram, we can see like request token 0, 1, and response token 0. And we also have the other metadata, just like temperature, seeds, everything that's also cached at the front end. So in case a migration is needed, all of those information are available for worker 2 to continue. So this wouldn't really impact.
Yeah, and I think it's also, I think we can't guarantee, I think, exact the same, because of the seeds and things that, the randomness of each individual worker. But I think, as Jack mentioned, we'll still hold to the same temperature and the same sampling parameters.
Yeah, that makes a lot of sense. Let's continue.
Cool. Let me move forward. Okay. So as I mentioned before, I think no matter what, there's going to be failures in the system. So we really want to be able to guarantee what we think of as high availability. And what we mean by that really is that you can have multiple replicas of any component in the system. And that if anything goes down, only that piece needs to be restarted. Right. We call this the cascading failure. So we don't want it to be that if one decode worker goes down, we need to restart all the prefill workers, right? Or all the decode workers, right? But of course, that's easy to say. How do we go about proving that, right? So one of the things that we've been investing in is what we think of as a fault injection test framework. So this is a Kubernetes-based tests where essentially we will deploy Dynamo under any type of different configurations, start sending in requests, inject a fault, and then measure exactly what happens, right? How many failures we see, how long it takes to recover, right? And so we have a cool little demo to show that as well. And let me go ahead and just play this through. And so you'll see it's a PyTest-based framework. And again, we provide this in our GitHub for other people to extend as well. In this particular example, we're going to be doing an aggregated deployment, but we're going to have 2 of everything, right? So our goal in this test would be that we actually see minimal failures, right? Because as we already told you, we're going to be routing around anything that happens. So at the beginning, we deploy it, we see that it's ready, we start sending in the requests. And in about maybe 10 seconds in, we're going to inject a failure. Okay, so now you see that there's actually a failure been injected. In this case, we're deleting one of the decode workers, right? And trying to see, again, how does the system respond? So then we continue sending in requests, and any potential requests that happen during the failure also get affected. And we buffering. So they made me move closer to the end. Let's see if that works.
I guess while we're figuring out the buffering, there's some questions in the chat. Can this architecture be used in the future for dynamic request migration, such as like proactive migration, not only in worker failures, but also in load balancing or cost optimization scenarios? So in other words, does the system itself plan to migrate to the most efficient worker by itself?
Currently, we actually pick the best worker to handle the particular request. So basically, we assume you have a pool of pods that's already up, and then if you have the pod that is up and running using GPU resources, if you're not sending requests to those workers, then I assume they just sit idle at this current moment. So we also have like KV router that can pick the best pod that has the most up-to-date KV cache so that we don't compute as much as we need it when giving the request. And in the future, like if we decide to switch over to a different machine, because for example, the current machine is costing, I'm just making it up, say $100 an hour, and then we find a machine that only costs $1 an hour, then we definitely want to shut down the more expensive machine. And if there's any ongoing request, we want to migrate them to other machines that are able to take it right away. And throughout the process, the whole migration decides to make sure the user don't notice anything. It's just seamless, like nothing has happened in the data center.
So obviously it's seamless, but are there any like performance trade-offs? Somebody in the chat asked if there's any trade-offs in the way that we actually do request cancellation and migration.
In terms of migration, there will be a bit of trade-off because the first worker will be doing all the previous stage. So it already did the expensive work that generates the KV cache. And then if we are just doing a graceful shutdown and then we want to move the ongoing request to another worker, we are able to, in the future, we're able to copy the KV cache to the new worker. And then we don't have to redo the prefill. But if it's due to a disconnect, for example, the worker just have a power failure, it just goes out, then there's no way we can recover any state in the worker. So everything will just have to be recomputed. In terms of cancellation, we just basically just send the cancellation signal to the worker, and then we'll have the worker just to stop processing the request on the next batch.
And actually, cancellation should have the opposite effect, right? So as opposed to hurting their performance, it should allow you to be able to save room for the actual meaningful requests, right? As opposed to continuing to handle things. And the other piece is that these things are configurable as well, right? So if request migration doesn't make sense for your use case, you'd rather just fail them, that's also possible. So we're not going to do it behind your back. And so.
Yeah, I think Jackie touched on something really key but subtle there. When he mentioned the KV router under the hood could be used in conjunction here. So a goal of what we're building here is composable pieces all around. And where Dynamo really shines is when you bring them all together, right? You can take what you want. You can take some, leave some based on your needs. But for example, in this migration scenario, if you hook everything up together and we have KV routing selecting the next worker to handle the request, you can try to make some optimal decisions there. If we say migration doesn't necessarily handle transfer of KV state, but you've also turned on KVBM with your worker, where that can automatically detect the available KV state somewhere else in the system on disk or on CPU. That can also synergize. And with all these things together, you can ultimately keep your latencies low and your throughputs high.
All right, Neely, how about we hop back in
Exactly.
to the rest of the presentation?
Sure. If we can use the screen again. Yeah, so I will just show kind of how the end of the test looks like, just to give a feel for how it is. Again, our goal is to make sure that, in this case, because of the high availability, that there's really limited failures during a failure detection here. So you can see exactly that. So we have this amount of time to start up. We have this number of requests before, just to make sure that there's no failures before we even injected something. And then you can see afterwards we have one failure. Right. And we can also calculate the request time. So again, main thing is that we're looking for ways to not only provide high availability, but also provide tests that kind of continue to ensure that as we go forward as well. And how we're doing on time? Do we want to go through the observability pieces, or?
Yeah, we have a couple of minutes, so we can definitely go over this and then get into the roadmap after as well.
Awesome. So I'll just kind of continue on. So in the spirit of, having to handle failures, even when they happen, and even if we try to prevent them, we also want full visibility into the system, so that not only can you tell when things are going right, but when things go wrong, you can kind of try to see what exactly is happening. So we provide both software monitoring, so requests per second, time to first token, as well as hardware monitoring, leveraging standard tools like DCGO. Another piece is logging and tracing. So we have full kind of span tracing between all the different components in the system. So you can see that in the logs, you can kind of correlate between the front end, the decode worker, and the prefill worker. And finally, the coolest part about that is we also integrate with OpenTelemetry, right? So not only from the logs, you can find out all the different types of information and error cases there. You can also see the actual spans, right? And this gives you a lot more visibility into how long things are taking. In particular, you can see for this type of request, the decode portion was taking much longer than the prefill, for example.
Okay. Neely, a quick question on this. What's an example where I would want to know such detailed information? Like, what type of information would I want to dig into, and why would I want to dig?
So I think, just like we said, failures are going to happen, and there may be certain types of load or separate types of traffic that you didn't anticipate, right? And when that happens, you may have, let's say, SLA violations. So your time to first token suddenly becomes huge in terms of spiking. What you could do is start to dig into, let's say, one of those ones that have violated your SLAs, and then see for that particular trace where in the whole distributed pipeline are you falling down, right? Is it the decode worker that's taking longer, or is it the prefill worker that's taking, or is the front end hammered, right? So we've seen cases even when the front end is not given enough CPU resources that it can become the bottleneck. So really, it's an investigative tool.
I see. And if I wanted to dive even deeper, like maybe there's some custom region I want to know about. Maybe I've implemented my own Dynamo worker because Dynamo is just that composable and hackable. How would I sort of integrate into that?
Yeah, so we offer, so in the Dynamo runtime, we have APIs where you can inject your own custom metrics and add those, and they'll be exported in the same way that the rest of the metrics are. Same thing for spans as well. And because we are leveraging OpenTelemetry standards, spans should work also from your internal spans as well. One of the other things we're working on is integration to show how do we use this with Insight as well, one of other NVIDIA's lower level tracing tools.
Yeah, that'll be the final boss when we get Insight finally hooked up.
That would be pretty cool. So just really quickly on next steps and roadmap. One of the things we want to ensure is that we have parity with the backend framework. So even though we're wrapping and providing additional capabilities around SGLang and VLM and TRTLM, we also don't want to hide information, right? So we're working very carefully to make sure we can still have the same logging that you're used to from the frameworks directly, same types of metrics, and as Ryan was talking about, same types of tracing. So logging and metrics, I think we have a full handle on. Tracing is one of the things I think we'll still need to investigate how to make sure that that's happening. From cancellation, we're looking at how do we even cancel requests earlier. So we saw cancellations generally after tokens were already created in the front end. We're looking at how do we cancel even before that, before pre-processing happens, because even that can be expensive. Request rejection, how do we prevent the system from going into an overlaid state? So looking for ways to do that at the token level and request level. And finally, one of the coolest things, again, we spent a lot of time detection and resiliency. Now we're also turning our heads towards recovery, right? So in the cases where we need to recover instances, how can we do that as fast as possible? And as Anish mentioned, this is an open source project. And so we're excited to be collaborating with everyone out there. And so if you're excited about this as well, feel free to join us and contribute.
We have a ton of questions in the chat to go over. So Yeah, when a node or GPU is holding part of like the KV cache that fails during like a worker going down in LLM inference, what are some of the strategies or runtime mechanisms that we recommend to preserve, low latency recovery, particularly for like pipeline parallel or tensor parallel workloads, without having to duplicate the full cache or re-execute the previous tokens?
Yeah, I think I could probably take a first pass at this one. Maybe pass it around after. But yeah, if you heard of the KVBM, KV Block Manager feature, essentially it's unlocking a larger pool of storage for KV cache blocks, so CPU, disk, remote storage, etc. But the really nice part is that it integrates directly into the frameworks and the schedulers inside the framework. So the every forward pass on the model in this like auto regressive generating token by token, every time it needs to add a block or evict a block from its own, like say TensorFlow TLLM or SGLang, for example, their notion of what the KV cache is and what it has available, that communicates out to KVBM and to all this other mechanisms hooked up into Dynamo. So if a request gets halfway through generation and it's used certain blocks from prefill and it's generated new blocks while decoding, those can be offloaded during inference asynchronously in the background. And if a failure were to happen, they should still be there in KVBM, accessible for the next worker to pick up.
Yeah, I'm definitely looking forward to that. I think this is going to be a very cool piece of technology. And as you said earlier, how the whole system integrates with all the different components. So the KV Block Manager is really awesome stuff.
Yeah. We got another question from Sensor Datas. Migration limit parameter can be configured on a model by model basis. However, if there's consecutive small outages in the long production runs of a model, how does the system itself behave when the limit is exceeded? Are there any like fail-safe fallback mechanisms that are engaged without disrupting the ongoing token state itself?
So the question is about if we are setting a migration limit to say migration free, and then for some reason, when a request is received by the front end, and then it tries to talk to worker 1, and then it got disconnected, so we only have 2 more chances left, and then we got migrated to worker 2, and then for some reason it fails again, and then it got migrated to worker 3. So in this scenario, well, I would recommend just set probably a larger migration limit in this case, because if we know that we need multiple numbers of migration, we just want to set a large enough number so that it's covered.
Yeah, I think currently, like the follow-on to that question was, how does it behave when the limit's exceeded? So it should generally act as if you didn't use migration at all. Like a failure is a failure. You should get a graceful error on the client that, maybe some 400 or 500 server-side error in this scenario. In terms of a fail-safe, I think, like Jackie said, you could tune based on what you know about your deployment that maybe X limit should be enough. But maybe sometime in the future, there can be something more intelligent, like if we're noticing rapid failures, like enable or disable this behavior dynamically. Like maybe you don't want it to fail 100 times. If we dynamically detect that a lot of failures are expected, and you actually just want to fail earlier, get your resources back, save your user or client like the time they'd be spent just getting failures over and over. So yeah, definitely something we could do there.
Cool. Maybe one last question before we end the stream.
Yeah, that'd be great.
Does Dynamo help with optimizing offline inferencing use cases? I'd assume like batch inferencing probably here.
Yeah, I can take first pass. So there's not a whole lot about most of the features we've described that are unique to online. You can have your system running. You can be queuing up large numbers of requests, like maybe a common scenario, something like document summarization, and you have these huge contexts, and you're not particularly latency sensitive, but you just want to get an answer, right? Things like KVBM, things like KV routing, if you have a bunch of offline workers and a bunch of documents, like these all still synergize and still add value, regardless of whether you're sensitive to the latency or not. But yeah, maybe Nile, you have something to add there?
No, I was going to say that's exactly right. I mean, I think the part that we can do is, I think, around that KV state management. So I think in general, we see that as being the most expensive piece in the system, right? So if you can avoid recomputing that either through KV block manager or through KV routing, those techniques should apply in batch settings as well as online settings. I don't see why they wouldn't just apply.
All right. Well, that was a pretty fantastic office hours. I think we learned and we're able to present so much on the progress for what we're doing and how we're handling fault tolerance. But there's so much more to do, right? And so I think that roadmap itself is pretty insightful, and I know we all have a lot of work to do to keep maintaining it. What seemed really interesting as a common theme that kept coming up was KVBM. So maybe our next office hours can be about how KVBM has been developed since we last presented it at the Base 10 office. But yeah, in general, Dynamo itself is like releasing every 2 weeks. And so, we're an open source first project. You can check out the latest releases as we're moving on. As Nilay mentioned, you can also, test out a lot of these fault tests and scenarios yourselves on Kubernetes. So you can spin up a Dynamo deployment, batter it with a lot of these scenarios that could result in faults, and then notice how the system itself behaves and responds. And ideally, you want it to configure in the way that makes sense for your business use case, right? Or your production use case. So if you have feedback or you want to see more features or something that you don't think we're thinking about enough, feel free to open up GitHub issues. Ryan's one of the most active people that I know, but we're all reading the GitHub issues as well. So yeah, on that note, like I said, we're an open source first project. So GitHub is a great way to chat with us, ask questions, get our eyes on certain features. But the Discord is also a very great way to engage directly with us and have some longer conversations as well. But yeah, with that said, thank you guys so much for tuning in to our office hours today. We'd love to answer more questions, so please don't be shy again. Use the GitHub, use the Discord, get in touch with us. But yeah, and one final plug for GDC DC. It's going to be an awesome event. And so I know we're going to have some Dynamo reps there, some people on the Dynamo team presenting progress, but there's so much more happening in NVIDIA. So would highly recommend, scanning the QR code. And if you're out on the East Coast or can make it out there, definitely feel free to attend. Yeah.
And come contribute to Dynamo.
Awesome.
We want your help. We want to work
Indeed.
together.
Indeed.
Yep.
All right. Thanks, everyone.
Alrighty.
Thanks, Anish.
Thanks, guys.